This is Justin Sojourner representing Team 14 Visionary Viaduct Engineering for the Spring 2019 Civil Engineering 495 Capstone class. Our team at Visionary Viaduct Engineering was tasked with the demolition and reconstruction of the Hollister Street Bridge, along with the removal of undocumented fill from the nearby Brown property. The existing Hollister Street Bridge, shown here, is approximately 820 feet and made primarily of wood. The bridge has long lived its purpose in serving the county of San Diego. We have answered the county's demands, and the new bridge will have an equestrian lane, wider shoulders, and a pedestrian sidewalk. After further research and analyzing the needs from local law enforcement and first responders, we decided to demolish the bridge in 2 phases. The reason for this is because Hollister Street is the only efficient route to get to the community south of the Tijuana River, and closing that access can add up to 10 minutes of response time. It is estimated that approximately 35,000 cubic yards of unclassified fill material was placed on the Brown property by a previous owner and now needs to be removed. The removal of the illegal fill is important for the local area as its placement on the property is believed to have an adverse effect on flooding in the surrounding area. Studies on how this fill removal will affect the bridge design and the surrounding hydrology were conducted. Shown is our project personnel. They will introduce themselves to you throughout this presentation.
Hello, my name is Daniel Olague, and I was in charge of the hydraulic analysis. For the hydraulic approach, HECRAS version 5.0.6 and data from the San Diego County Flood Control District was used along with a HECRAS analysis on the Tijuana River that was already conducted by the United States Army Corps of Engineers. From the HECRAS analysis report done by the United States Army Corps of Engineers, a table was provided by the International Boundary and Water Commission giving the annual peak flows from 1962 to 2015. As you can see, the trend after 1980 shows a gradual increase in peak flow. This trend is most likely due to urbanization, lack of vegetation, and clogging of flow due to debris and fill material within the Tijuana River watershed. Here on the top left is a picture also taken from the United States Army Corps of Engineers HECRAS analysis and how they created different reaches and stations for the Tijuana River. The other pictures are screen captures of geometric data of the river station containing the Hollister Bridge and Brown property area. This was found using data provided by the Flood Control District during the HECRAS analysis attempted.
Hi, I am Ricardo Ibarra, and I am the Environmental/Stormwater Engineer for Visionary Viaduct. I was in charge of the stormwater analysis for this project. The goal was to create a drainage system that will mitigate any adverse flooding effects from the newly built Hollister Bridge and on the removal of the fill of the Brown property. The goal is to generate no more runoff before development than after development. San Diego County Hydrology Manual as well as SanDiGES website was used to find the soil types in the site location as well as the rain intensity. The flow rate in the area was found using the rational method. After plugging in values into the equation, we found that the flow rate in the areas were 1.13 for the Brown property and 0.17 cubic feet per second in the Hollister Bridge area. In the inlet area of 0.13 feet squared and 0.75 feet squared on the concrete sewer pipes of 5-inch diameter should be installed to minimize the rain runoff from the site location. The purpose of the SWIP is to maintain water quality by keeping documentation and following BMPs for this project. Visionary Viaduct will oversee that everything in this SWIP is accurate and complies with San Diego County regulations. The project is being performed with County of San Diego, California jurisdiction. The SWIP has been prepared to comply with State Water Resource Control Board, National Pollution Discharge Elimination Systems, waste discharge requirements, and together these measures will minimize stormwater runoff and keep the construction site from receiving costly penalties. Most important, the job will be completed with minimal environmental impact.
Hello, I'm Edward Esguerra, and I was the project manager and geotechnical analyst for this project. The geotechnical approach to this project was to gather CPT data given by Dr. Professor Julio Valdez and be able to identify each layer of soil in the profile. Given the data on the left, I was asked to make these graphs on the right side. By interpreting these graphs, I was able to then identify each subsurface layer of soil, their respective parameters such as their friction angle and its classification, as well as if they were liquefiable or not. These parameters would be important for both my findings and my recommendations, seen on the next slide. So in summary, the geotechnical analysis showed that the subsurface layers were all susceptible to liquefaction and all sand layers. Soil is saturated with the water table being 2 feet below the surface. The illegal fill is approximately 7 to 10 feet in depth, and the illegal fill is mostly unusable according to local rangers. So my recommendations, in accordance to my findings, were the substructure design should consider that all layers are liquefiable, possibly drilling the substructure all the way to bedrock and to account for that in their design. And for the grading of the brown property, to not exceed an angle of 40 degrees in accordance to the friction angle of the soil.
Hello, this is Bryan, and now we'll be going over the substructural part of the structure report. First, we'll start off with the structural approach for structural report. Chapter 13, Concrete Columns from Caltrans Bridge Design Practice, 4th edition, and ASCI 318 were used as guidance for column design. And for pile design, Chapter 16, Deep Foundations, Dr. Valdez's CIV 465 reader and Edwards' analysis of the cone penetration test data were all taken into account. Now we'll go over the structural findings for substructure. For column design, due to having a construction plan in which the bridge will be cut based on the center line striping rather than the center of the bridge, the columns needed to be designed to hold 60% of the total load. Due to this, the columns were designed to be 37 inches by 37 inches with a length of 20 feet. The column was then reinforced with 16 number 8 rebars and a number 4 tieback to prevent shear. For pile designs, because of the amount of load imposed by the bridge, it was decided to design deep foundations. The piles will be square piles and made out of concrete with a side length of 1.6 feet and will be 14.5 feet in depth. A pile cap will be used to connect the columns to the pile. The square pile cap is to be made out of concrete, being 96.7 inches by 96.7 inches with a thickness of 32 inches.
My name is Argamaso, and I am the structural engineer responsible for the design of the superstructure of the new bridge. To design the bridge, we used the bridge design practice posted in February 2015 by Caltrans, specifically citing Chapter 7, which talked about the post-tension concrete girders, and Chapter 10, which discussed the design for a concrete deck. In order to come up with a preliminary design for the bridge, we needed 2 parameters which were discussed earlier. The first parameter was the width of the new bridge, which was to include a new equestrian path, a new sidewalk, as well as the extension of existing shoulders. This new width came out to 54 feet. The second parameter we needed was the longest span at any point along the bridge, which was discussed by our structural engineer responsible for the substructure. The longest span came out to 94 feet. Using these parameters, we were able to come up with a preliminary design for the bridge, and then after that, we are able to test the bridge to make sure that it would be able to withstand any moments and forces that it may experience throughout its 70-year expectancy. A preliminary design for the bridge is made based on the parameters just discussed, and we found that we can use 7 girders with an overall depth of 4.75 feet for the structure, and that we can use 7.5 inches for the deck thickness and 6 inches for the soffit thickness. Next, we estimate what the jacking force of the overall bridge is going to be so we can continue with our calculations. A pre-stressed cable path is determined based on this preliminary jacking force, and then calculations are done to confirm that the jacking force we estimated still holds true, which we did to be 7,762.5 kips. Finally, calculations are done to ensure that the bridge would be able to resist all moments and forces that it's going to experience in its lifetime.
Hello, my name is Kenneth Gervacio, and my task for this project was to estimate the overall cost of the bridge. As you can see, our total project cost comes in just above $11.5 million. Of that $11.5 million, the bulk of the cost came in the form of bridge construction, roughly $8.7 million. The second bulk came from Esguerra estimate, which is roughly $1.6 million, and accounting for the fill was roughly $1 million. Next, our bridge demolition came in at around $200,000, and then lastly, our temporary structures, utilities, and equipment came at just under $40,000. The figure on the left shows a more in-depth breakdown of the overall bridge construction cost. Unit costs for this estimation came from the Department of Transportation, the County of San Diego, as well as national material prices. In conclusion, we at Visionary Viaduct Engineering are confident in our design and reports and hope to work with you again.